In the field of experimental dynamics, we're often interested in measuring the vibrations and dynamics of structural systems. And depending on the kinds of physical information we're interested in, we can use different kinds of sensors. Some examples of sensors include accelerometers, load cells, strain gauges, and etc. Now, when you take one of these sensors and you hook it up to a computer and start measuring, the first thing you start noticing is that you are measuring in volts and millivolts. And that doesn't really have direct correspondence to the physical units you had in mind. So if you had a load cell, you were probably interested in measuring forces in the form of newtons. But what you get is millivolts. So this is where this notion of sensitivity value comes in, where you can take this value, multiply it by the measurements you have in volts or millivolts, and really identify what the actual measurement is in the physical units you have in mind. So a sensitivity value is a physical unit of interest, such as newtons divided by volts or millivolts. Now, when you buy a brand new sensor, such as a brand new load cell, usually the manufacturer tells you exactly what the sensitivity value is. However, over time, the sensitivity value is subject to change. Temperature fluctuations, different kinds of experimental environment situations can certainly change the sensitivity values. So today, we are going to go over a number of experiments that we can do to help us classify and identify what these sensitivity values are. And we will do sensitivity value identification for load cells, accelerometers, and test hammers. And test hammers are pretty much another kind of load cell with a very different kind of application. So I hope you enjoyed this video and learned from it. So for the experimental testing that we're doing today, we're going to use a VibePilot, which is a fairly powerful vibration and dynamic signal analyzer. We're going to use a power supply box for the capacitive accelerometer that we're going to use, and there will be a laptop which runs SO Analyzer software, which has correspondence with the VibePilot that we'll do everything off of. Okay, we're going to start off by talking about accelerometers. Accelerometers are typically either capacitive or piezoelectric. Capacitive accelerometers work based on the concept of mutual capacitance, and in these accelerometers we typically have two plates that are negatively and positively charged, so we can have one that is fixed and one that is moving and that has mechanical properties. And so because they need to be charged, we need to have a power supply, and there is typically a dielectric material in between, and you can think of this as an electrical insulator. Now, capacitance here is proportional to the surface area of these plates and inversely proportional to the distance between the plates. So when these plates move, the voltage we measure is also changed. Now, because of this property, these accelerometers are able to measure static acceleration. Piezoelectric accelerometers work based on the piezoelectric properties of certain crystals, where the electrical state of the crystal is tied to the mechanical states of the crystal. Now, in these accelerometers, we typically have weights which move and alter the mechanical equilibrium of the piezoelectric crystal, which results in an imbalance in the electrical equilibrium of the crystal. So we can then measure positive or negative charges depending on the movement of the weight and the directionality of the movement. So now we're going to talk about calibrating for sensitivity values. The first method that we're going to introduce is called gravimetric static calibration. This is a very simple method that uses the Earth's gravity as a reference for calibrating a capacitive accelerometer. So we talked about how capacitive accelerometers use capacitive plates that are able to measure static accelerations. So let's see how this applies. We're going to take one of these accelerometers, put it on a table, and then start recording. And as we're recording, we're going to flip the accelerometer on its head in a backwards position. So what we end up getting is we're going to measure voltage values that are going from configuration 1 to configuration 2, and what we are interested in is identifying what the delta V, or the difference in voltage, is between these two configurations. Now, because we're going from minus 1G to plus 1G, we need to also take this delta V value and divide it by 2G. So this is a very simple way that gives us the sensitivity values for capacitive accelerometers. And by the way, for the experiment that we're going to do, we're going to demonstrate and show that this method doesn't really work for piezoelectric accelerometers because they can't measure static acceleration. So I have two accelerometers in front of me, capacitive accelerometer and the piezoelectric accelerometer. The capacitive, due to the way it operates, it needs a power supply, so I have this box right here, which helps us out. But at the same time, both of them are connected to our Vibe Pilot, which is able to send and receive the signals that we desire. So what we're going to do now is we're going to put these accelerometers down in the axis that they operate, and we're going to then flip them over on their heads backwards. So if they are able to in fact record the gravitational pull of the Earth, we'll be able to invert the direction of that measurement by simply inverting our accelerometers. So now we're going to go see how the results look like. So we open our SO analyzer into the configuration menu and we look at these transducer channels. So here we have a capacitive accelerometer that we're measuring the response for, and we also have a piezoelectric one. And for me, the input mode for the capacitive accelerometer is set to voltage and the coupling is set to DC ground. And the piezoelectric accelerometer is set to ICP and to AC ground. We can ignore these menus. Okay, so for sampling purposes, the sampling rate that I have is 2000 Hertz, and the block size is 128, and I'm going to measure 20 seconds of data. And the triggering will be free run because I like to start recording manually. That's really what that means. And so the only things that I have to do now are just to ensure that I am measuring time record and it's getting saved to the workspace. Okay, so on the left side we are looking at the response of the piezoelectric accelerometer, and on the right we're looking at the capacitive accelerometer. I'm gonna go ahead and start recording now, and I will flip the accelerometers, invert them so that we're able to see whether they can measure the gravitational pull of the Earth or not. Okay, so now we're going to flip them over. Now what's clearly visible is that with the piezoelectric, we're not able to see that shift, that translation in the signal, whereas with the capacitive, we're definitely able to see it. And so this tells us, yes, the capacitive accelerometer is indeed able to measure the gravitational pull. So we looked at piezoelectric accelerometer and we looked at the capacitive accelerometer. And with the piezoelectric, we start off at 0 and end up at 0. So of course we can't, this is indicative that we can't measure static acceleration. And there's a little bit of motion here in the middle. This is because I was trying to flip the accelerometer on its head. With the capacitive accelerometer, we were in one state when we started, and we ended at another state. And this is simply because we're going from plus 1G to minus 1G. And we can calculate the delta voltage, the change in voltage between the two. We are getting a voltage measurement of 1.94. Dividing this by 2G will give us the following sensitivity value for the capacitive accelerometer. The next method we're going to talk about is called Gravimetric Freefall calibration. This is a method for approximating sensitivity value of an accelerometer, and this process is different from the previous because it can give us the sensitivity values for a piezoelectric accelerometer too. So here we have a mass that is suspended in this apparatus that is comprised of the piezoelectric accelerometer down here. There is an unknown mass, and there's a load cell here. And this load cell will be used for the next part of the experiment. And everything is suspended from the string up here where we have this junction point. So when we hit at the location of the junction point with a hammer, what happens is that the string here carrying the mass will go into a slack, which creates this free fall effect on the mass that is down here. And so when the string is once again taut, the acceleration that the mass was experiencing, and when you're in a free fall, of course, this acceleration is 1g. And so when the string is taut again, this acceleration will be experienced by all these masses, which includes the accelerometer down here. And so our accelerometer will be able to measure the 1g, and we'll get responses that look like this. So we'll go from the equilibrium position into free fall, and this is the moment when we experience the 1g in the accelerometer, and we'll get a similar response in the load cell, and we'll talk about that later. And so for a response that looks like this, what we can do is we know that this position is 0. This is the equilibrium position. We know that we have some sort of voltage that we're reading. Let's say this is read in millivolts. And so what we can do is we can simply calculate the sensitivity of our piezoelectric accelerometer. So we're going to say sensitivity of accelerometer is going to equal to the value we're getting in millivolts divided by 1g. And so this is a fairly accurate way of assessing the sensitivity values for piezoelectric accelerometers. Now let's see how it will look like in the experimental side of things. All right, so we have an apparatus in front of us, and this is our gravimetric calibrator, and we are going to use this notion of gravimetric freefall calibration in order to identify the sensitivity of our piezoelectric accelerometer. So what we have is we have our device suspended from the string here. There is a load cell which we will use for the next part of the experiment. There is a mass which is unknown, and we have a piezoelectric accelerometer down here, and this is what we're going to find the sensitivity for. And what I'll do is I'll have my hammer, which I'm going to hit at this junction point, and we're going to have the acceleration results recorded along with the load cell measurements. And I will do this a couple times because I want to average my responses. So now we have our SO analyzer opened, and we click this configuration option, going into next. We are recording the responses of the first two channels. The first one is the load cell, and the second one is piezoelectric accelerometer, and the input modes are set to ICP, and we are recording the voltages. And so for the results, what we can see is that we're going from the equilibrium position, which is right here, into the free fall position, which is right here. And this here is the position at which the accelerometer is able to experience the free fall, or the 1g. And so we measure this value, and it's roughly 101 millivolts, which we then divide by the 1g, and we get 101 millivolts per G for the sensitivity of the piezoelectric accelerometer. The next method we're going to talk about is called gravimetric force calibration. This is exactly the same process that we followed for calibrating an accelerometer, but this time we're calibrating a load cell. So here we have an apparatus where we know what the mass is that is hung from the load cell. This is our load cell, and this is the suspension setup that we had from the previous experiment. And so we have this junction point. We're going to take our hammer and hit it down here, and we typically get a response that looks like this. So we're going from the equilibrium position into free fall, and this is the moment when the gravitational pull is experienced by the material, by all these masses here. Now, because this is a load cell, it's in fact not measuring the acceleration. It's measuring forces. So given the fact that we know what the mass down here is, this is a known mass, and given the fact that we know our pull is 1g going in the downwards direction, then we can calculate the sensitivity values for this load cell, which should have units of millivolts divided by Newton. So we could get a sensitivity value. We're going to call this load cell is equal to this increase, which is millivolts divided by mass times acceleration. So the acceleration is of course 1g, and the mass is given to us, whatever numeric value it has. And we're going to demonstrate this experimentally as well.
Okay, so now we're going to look at gravimetric force calibration, because this time we have a load cell in front of us and we want to find out what the accurate value is for the sensitivity of this load cell. We have a known mass that is attached to the load cell via an auxiliary line. This mass is exactly 96.07 grams. And you know, of course, here the auxiliary line will have a mass of its own as well, but for the sake of this experiment, we can assume it's quite small. And so we're going to take our hammer from the previous experiment and we're going to impact at the junction point and do this a couple times so we can then average our results and have a fairly accurate assessment of the sensitivity value.
All right, so this is, again, the position of the equilibrium going into free fall, and this is the moment when the 1g hits, and I need to know what my mass is so I can multiply it by the 1g. And so when we look at the sensitivity equation, we have this 11.7 millivolts for the step that is caused by the free fall, and we also know what the mass is. It's 96.07 grams, and by doing this arithmetics, we're able to identify the sensitivity value, which is millivolts to force. Test hammers are another class of measurement devices that are used to excite a structure with. This is a test hammer down here. These are also called impact hammers, force hammers, and they are pretty much load cells that we use to excite a structure with, because sometimes we want to know what the input force into a structure is. Now, to calibrate one of these devices, we need to create a pendulum apparatus with the accelerometer that we used in the previous experiment. So this is an accelerometer that we have here. We know what the sensitivity value for this accelerometer is. And so we take our test hammer and we go ahead and hit the pendulum with it and let the pendulum vibrate. And then we use the relationship between the acceleration recordings and the force recording, and we also need to know what this mass is. So let's call this m. So assuming that we know this m, we also know the acceleration sensitivity, or the accelerometer sensitivity, then we have all the information that we need to be able to calculate the sensitivity value for the test hammer. So we know what the raw voltage values are for both the accelerometer and the test hammer. Let's call this voltage accelerometer, voltage test hammer. And so this ratio can be calculated as R is equal to VH over VA. Now we are pretty much set and ready to go and calculate the SH, which is the sensitivity for the hammer. This will have units of millivolts divided by newtons. So if I'm doing my arithmetics correctly, I will have R multiplied by sensitivity of the accelerometer divided by m. And so this should give us exactly what the sensitivity of the test hammer is, and we're going to illustrate this process experimentally next.
All right, so this is my test hammer. It's got the load cell in front of it, so upon impact it's able to measure forces. And I want to now identify what the sensitivity of this test hammer is. And so to do this, I have a pendulum apparatus in front of me comprised of the piezoelectric accelerometer we identified the sensitivity for earlier, and we have a known mass. So what I can now do is I can bring into impact my test hammer with the pendulum, and from the measurement results and some of the parameters we already know, we're able to identify what the sensitivity of the test hammer is. Now, going back to our SO analyzer, we want to go back to the configuration panel again, and this time we're going to have the hammer, which replaces the previous load cell, and now we have the piezoelectric accelerometer turned on again. So we have two responses that we're measuring. Both of them are in ICP mode, and we will press next, and I don't think we really have to change anything. I'll probably change the total time to 10 seconds. I don't really want to go through 20 seconds again, and this will be free run again. And that's it. Press OK. And of course, the last process in this whole experiment is to do the actual experiment, and we press the record option. This is 10 seconds, so quickly we take the hammer and boom. And of course, we would have to repeat this a couple of times to get a more accurate assessment of the sensitivity value.
So when it comes to the experimental results, what we're interested in is the values of the voltages from the hammer and the piezoelectric accelerometer. These are impulse type loads for the moment of the impact, and we record these values. They turn out to be 97.2 millivolts for the hammer and 826.5 millivolts for the piezoelectric accelerometer. We also need to calculate this ratio, which is the ratio between these two numerical impulses, and then multiplying by the sensitivity of the piezoelectric accelerometer and dividing by the numerical value of the mass, which in this case was 469.8 grams. And this gives us the sensitivity value for the test hammer. Now, what's interesting to notice about the pendulum setup is that the configuration of the auxiliary strings that are used to suspend the masses, so we have one kind that looks like this, we have another kind that looks like this. This configuration actually matters when it comes to measuring acceleration data. So here in configuration A, we have a parallelogram motion, and we also have in configuration B a pendulous motion where the strings are simply tied differently. Now, we're going to see that the accelerations that result from the measurements we're getting from the accelerometers will be completely different, just simply because of this tiny change that we have in how we attach our suspension to the support rod. So in both cases, we start with the masses being at equilibrium, and when we bring the mass into motion in each case, we are introducing a rotation in the arm of the pendulum and the displacement in the mass. Now in the parallelogram, when we measure the acceleration from the accelerometer, what we're measuring is the horizontal acceleration, whereas when it comes to the pendulous motion, we are measuring the response in the direction that is tangential to the circle of the pendulum. Now, what's interesting about this tangential acceleration is that it gets canceled out by the gravitational acceleration. So gravity goes in the downwards direction, but it also has a horizontal component that is parallel with the tangential acceleration. And so when we are looking at the pendulous setup, we get very tiny accelerations, and we might even have cancellations of the acceleration altogether. These here are the responses of the pendulous motion and the parallelogram motions. And this is interesting because this really is an illustration of how experiments can confirm what we had theoretically derived. So we have the motion of the pendulous configuration, and we also have the parallelogram motion. And so what's clearly visible is that the pendulous motion is almost negligible, almost close to zero, because of that cancellation that we talked about when the tangential acceleration interacts with the gravitational acceleration. In our last experiment, we would like to look at the transverse sensitivity in accelerometers. When you vibrate an accelerometer in the axis it was not supposed to operate, we can still get measurements. This is due to the transverse sensitivity of the accelerometers. And when you go out there and buy an accelerometer, the manufacturer usually tells you what the transverse sensitivity is. Now, to find out what the sensitivity is experimentally, we have to have another gravimetric apparatus where we bring the accelerometers into free fall and we look at their out-of-axis measurements. So here we're going to have an experimental setup with 3 accelerometers, number 1, 2, and 3, with the third one measuring in the vertical direction and the first 2 measuring in the horizontal direction. Now we get the voltage values for V1 and V2, and we average the two, which results in their longitudinal acceleration measurements being canceled out. So we say V horizontal average is the average of V1 plus V2. So by doing so, we are canceling out the longitudinal accelerations, any kind of experimental accelerations that result in the horizontal direction. But what we're left with is the transverse accelerations that these two are measuring, resulting from the free fall. And this is our free fall. We also have V3, which is the vertical acceleration. And this voltage value, of course, has correspondence to 1G. So we can get the sensitivity in the vertical direction, which is V3 divided by 1G. And of course, the units should be millivolts divided by G. Now, we are going to take the ratio between the horizontal voltage and the vertical voltage. This ratio is equal to V horizontal average divided by V vertical. And we will take this value and this will help us calculate the transverse sensitivity. So this is transverse sensitivity is equal to this ratio multiplied by the vertical sensitivity. And if we do the arithmetics correctly, this should give us millivolts divided by G as well. So let's see how we can do this experimentally.
And this is our experimental setup. We have 2 horizontal accelerometers and the vertical accelerometer at the bottom, and everything is suspended from this junction point, and all we really have to do is to reiterate what we did before, take the hammer and hit it at the junction point. And of course I'm going to do this a couple times so that we can then average our results. So I'm going to the configuration section in SO Analyzer, press next. And here, what you can see is that I've added 3 piezoelectric accelerometers. All of them are in the ICP mode. We have piezo vertical, piezo horizontal 1 and 2. And I think I don't really need to change any of the other settings. I've left the duration for 20 seconds. It's recording at 2000 Hertz.
So we pretty much go from the equilibrium position into free fall and into the moment at which the string becomes taut again. And this is when the accelerometer is able to pick up the 1G
that resulted from the free fall. And when we look at the accelerations in the transverse direction, I'm looking at the horizontal average plot, and we can see a similar type of impulse step going from the equilibrium into a higher state. The values are numerically given to us, and the next thing we got to do is to calculate the ratio between the transverse and the vertical directions, which is given by here, and we need to multiply by the sensitivity of the accelerometer in the vertical direction. So this is exactly that sensitivity value. This is I think we call this S3, or you can also call this S vertical. And so lastly, we calculate the transverse sensitivity, and it ends up being something like that. And when you compare these two numeric values, what you end up seeing is that the transverse sensitivity for these accelerometers ends up being roughly 0.17%. So it's good to keep this in mind as well whenever we operate accelerometers. So yeah, that's it.